Okay, Riemann sums. Well, the motivating question for today is, how can we approximate the value of a definite integral? After all, as I discuss in the book, there are many functions, such as these ones, that simply do not have elementary antiderivatives, which means that, for example, if you wanted to integrate one of them, say from 5 to 22, you cannot do it in the usual way. You can't use the fundamental theorem of calculus to evaluate this integral because there is no elementary antiderivative of this function. So if you do need to know this value for some reason, you will have to settle for an approximation. How can we do such a thing? And in general, how can we approximate the value of some definite integral of some function f from a to b, whatever those endpoints are and whatever the function is? Well, there are many ways to do it. And if you ever take a course in numerical analysis, you will study some of the most efficient ways. It's actually quite an interesting question, but we are not looking for the best ways, the most efficient ways to approximate a definite integral. We're just looking for a way that will satisfy us today. And the simplest way to approximate a definite integral is with a so-called Riemann sum. A Riemann sum is essentially a crude human attempt to approximate the work of our dear old friend, the integration demon, whom we first discussed long ago, back, I think, in the first video in this series. The integration demon, you will recall, is just a kind of poetic way of thinking about what an integral is, in the intuitive sense of an integral being a weighted sum of infinitesimals. Recall the basic idea. If we want to integrate some function f from a to b, what we are doing, what our integration demon is doing, is taking the region of integration here from a to b, disintegrating it into infinitely many infinitesimal pieces. Obviously, I can't draw infinitely many things, and I cannot draw infinitesimal distances, so this is just a schematic picture. But each one of these little gaps is supposed to represent an infinitesimal bit of the x-axis. And the length of one of those things is what we call dx, an infinitesimal bit of x. Well, the idea of a definite integral is that at each value of x in that region of integration, we surround it by an infinitesimal of length dx, take that little infinitesimal bit dx, and attach a weight to it, multiply it by a real number, namely the value of the function at x. So that instead of just looking at the infinitesimal dx, we look at f of x dx. And the integration demon visits every point in the region of integration, gets an f of x dx for each one of them, writes them down in his little book, and then adds them all up. And of course, that is what the integration does. It's an infinite sum, hence the stretched out s, of all the f of x dx's from a to b. And then, thanks to the magic of the fundamental theorem of calculus, we have generally been able to come up with exact expressions for the values of these integrals. But of course, we cannot always do that. And if we want to approximate an integral, as I said a moment ago, what we can do is to approximate what the integration demon is doing. We may not be able to shatter the region of integration into infinitely many pieces, each of which is infinitesimally small, and construct this infinite sum. We are mere pitiful humans. But there's nothing stopping us from breaking this region up into a finite number of pieces, ideally a large finite number, and for each piece we could take its length, multiply it by a certain weight, namely the value of the function at some point inside that piece, and then add those up. And that's all a Riemann sum is. It's a finite weighted sum, not of infinitesimals, but of small finite pieces of the region of integration. I'll show you an example. In fact, I'm going to show you an example of a Riemann sum for a function that we actually can integrate, just so you see how it works in a familiar case. In the book, I give an example where we do this with a function that doesn't have an elementary antiderivative. Let's do it a little differently here. So let's think of this integral, the integral of minus 2x squared plus 2, an ordinary polynomial, as x runs from 0 to 1. Now this is an easy integral, and if you do it, you will find that it comes out to 4/3. But I want to show you how we could approximate that value if, say, we did not know how to use the fundamental theorem of calculus. And we will do that by using a Riemann sum. let's think this through geometrically, which I think will help you understand the process. Here's a graph of the function over this interval from 0 to 1, where we will be integrating it. Now we are going to make believe we are like the integration demon. But slow, clumsy, all too human creatures that we are, we can't break this up into infinitely many pieces. We can only break it up into a finite number of pieces. We have only a finite amount of time in which to live, after all. Let's be very crude on this first example. Let's break this interval up into 4 equal subintervals. Each one of these guys is sort of like an approximation to our dx. But of course it's not dx, this is not an infinitesimal, not even close. Each one of these is a quarter of a unit long. So instead of calling this dx, I'm going to call it delta x, just an ordinary change in x, like you would talk about in a science class or something. Not an infinitesimal change, not the little dx, just delta x. And in this case, in fact, our delta x is 1/4. These points, for example, are at 1/4, 2/4, or 1/2, 3/4, and 4/4, 1. So if we're like little kids trying to pretend that we are integration demons, what would we do? Well, we would take each one of these subintervals, look at its length, which is delta x, 1/4 in this case, and we would attach some kind of weight to it. And then we would take all the weighted delta x's and add them up. And that would be our approximation to our integral. Well, let's do that. Our Riemann sum with 4 subintervals is going to look something like this. We've got 4 terms, one for each subinterval. Each term, we take the length of the subinterval, 1/4, and we're going to multiply it by some weight that has to do with the function on that subinterval. Here's the catch, though. Whereas the integration demon was dealing with infinitesimal subintervals of length dx, and he had it easy because the value of the function is effectively constant on an infinitesimal, we are dealing with finite subintervals, and the value of the function is not constant on those finite subintervals. Maybe it doesn't vary that much, like on this first one, the value starts up here at 2, and by the time we're done, well, it's a little lower than 2, but it does vary. So we have to decide where in that interval we are going to pick a so-called test point, i.e. the point where we will evaluate the function to get our weight, and we have lots of choices. But to make this simple, let's use the midpoints of our 4 subintervals as our test points. So on this first one, which corresponds to this first term, for the weight we attach to that quarter, let's evaluate the function at this point, which is halfway between 0 and 1/4, so of course it's going to be at 1/8. So the weight we will attach here is going to be the function's value at 1/8. And then we'll do the same thing at the second term. The length of this second interval right here is of course still 1/4, which is what we've got right there, but the weight we will attach to it will be the value of the function at this test point, the midpoint of the second interval, which is 3/8. So the weight here is going to be f of 3/8. Well, I think you get the idea. For this third subinterval, we take the length 1/4 and multiply by f of 5/8. And the last term is going to be 1/4 times f of 7/8. That point right there. Good. And now we have something that we can compute. And before we actually do that, take a minute just to be sure you understand what this sum represents geometrically. Take the first term, 1/4 times f of 1/8. Well, we can think of that as the area of a rectangle whose width is 1/4, namely the subinterval there, and whose height is f of 1/8, which is this length right there. So their product is the area of this rectangle. And to that area, we add the second term, which we can think of as the area of another rectangle of width 1/4 right there, and height f of 3/8, which appears right here. So their product is the area of this rectangle. And of course, the last 2 terms correspond to the areas of these 2 rectangles. So the full sum works out to the total area of those 4 rectangles, which, as we can see, looks like a pretty good approximation to the area under the curve, which we know corresponds to the integral itself. So it makes sense that this should be a good approximation to the value of the integral. And if you actually compute all of this, which is a little bit of a pain, but it's just arithmetic, you should end up with a sum of 43/32, or at least that's what I got if I didn't screw anything up in the arithmetic. But I'm willing to believe that I did it all correctly, because look, this is a very good approximation in to 4/3. And after all, 4/3 is 40 over 30. And here we've got 43 over 32, which is pretty close. In fact, if you run that through a calculator, you get 1.34375, which is very close indeed, because of course 4/3 is 1.33333333 repeated. This is within about 1% of the true value. And if you think about it, that is actually quite an impressive approximation. If we could get to within 1% of the true value by chopping our region of integration up into 4 pieces instead of infinitely many pieces, you can see how we could very quickly improve this approximation even more. For example, instead of cutting the region of integration into 4 pieces, why not chop it into 8? Once again, we could take our test points as the midpoints of our 8 subintervals, each one of which has length 1/8. Then we could set up our Riemann sum with 8 subintervals, our weighted sum of all those little delta x's, and that would look like this. A weighted sum of all those 1/8. The weights are the values of the function at the midpoints of those subintervals. So the first one here would be at 1/16. So the weight there would be f of a 16th. The next one would be f of 3/16, and on all the way down to the last one, which would be f of 15/16, evaluated at that test point right there, halfway between 14/16 and 16/16. That is 1. There are 8 terms here, one for each of the 8 subintervals, and if you do all the awful arithmetic, you end up with approximately 1.33594. And as we can see, that is even closer to the mark than our Riemann sum with only 4 subintervals was, which is not surprising, since each one of these terms corresponds to the area of a rectangle, and with 8 little rectangles, each of which half as wide as they were before, we can approximate the area under the curve even better. And of course, there is nothing to stop us from increasing the number of subintervals. We can go much higher than 8. And I'll make a quick table for you. And let's begin with what we just saw, that if we use 8 subintervals, then the value of the Riemann sum is about 1.33594. If we were to double the number again and go to 16 subintervals, the Riemann sum, which would now consist of 16 terms, turns out to have a value of approximately 1.33398. And there's no need to double. Let's just jump to 100 subintervals. If we do that, the Riemann sum's value turns out to be about 1.33335. And one more, if we go to 1,000 subintervals, then the Riemann sum's value is approximately 1.3333335. And naturally, the more subintervals you look at, the better and better your Riemann sum approximates the value of the integral, which we know in this case is 4/3. Now, I want to make a couple of points here. First, I obviously did not calculate that sort of thing by hand. I used a computer. And if you know even a little bit of computer programming, it's a good and straightforward exercise to write a program where you feed it a function and tell it to compute a Riemann sum with a given number of subintervals, and it will do it for you. That's what computers are good for. Lots and lots of very fast arithmetic. Okay, so that's my first point. My second point is that the value of the sum depended on where we took our test points. I used the midpoints because those tend to give you better approximations with smaller numbers of subintervals. But we could have used, say, the left endpoint of each subinterval as our test point, or we could have used the right endpoint of each subinterval as the test point, or we could have taken the point 2/3 along the way as our test point. That's entirely up to you, but midpoints work best, at least when we have relatively small numbers of subintervals. Which brings me to the next point, which is that as the number of subintervals increases, so that each individual subinterval gets smaller, it matters less and less whether you use the midpoints or the right endpoints or the left endpoints or whatever, because the smaller the subinterval is, the less room the function has to vary over that subinterval. In the extreme case, when we have infinitely many subintervals, as the integration daemon has it, then there's no room to vary at all. But even if we're looking at subintervals whose size is 0.00001 or something like that, the function doesn't have much chance to change its value over that subinterval, so it really doesn't matter where we take our test points, provided, again, the subintervals are sufficiently small, which happens when we have sufficiently many subintervals. And in fact, the idea is that each one of these Riemann sums is an approximation to the true value of this integral, and as the number of subintervals gets larger, that Riemann sum approximation gets better and better. In the limit, as the number of subintervals goes to infinity, the value of the Riemann sum goes, of course, to the value of the integral itself. And this brings us to another important point about Riemann sums. They're not just a method for approximating integrals. They can be used to define integrals in terms of limits without actually referring to infinitesimals. So let me show you how this works. Let's say we have any old function f defined over the interval from a to b. Let's say we want to integrate f from a to b, and the integration daemon is busy. So we're going to get our hands dirty and at least come up with an approximation to that integral by doing a Riemann sum. And rather than say, let's chop it into 4 pieces or 8 pieces or 1,000 pieces or whatever, let's just be very general and chop it into n subintervals. And the length of each individual subinterval we will call delta x, and since there are n of them, and we're assuming they're all the same size, delta x will be 1/n of b minus a, the distance from a to b. So delta x is b minus a over n. And now if we want to form a Riemann sum with n subintervals, well, we know the drill. It's just a weighted sum of all of these lengths. So we're going to have something like this. The first term will feature delta x, the length of the first subinterval, times some weight, which will be the value of f at some test point in that interval. The second term will start with delta x, which of course is the length of the second subinterval, to which we will then attach another weight, namely the value of f at some test point in that second subinterval. And so on and so forth, all the way down. There will be n of these terms altogether, and that will be our Riemann sum. But let's put some symbols in here for our weights. To do that, we'll need some symbols for our test points themselves. So let's let x sub I represent our test point in the ith subinterval. If we do that, then the weight in our first term, which corresponds to the first subinterval, would be f of x1, and the test point in our second subinterval would be x2, so that means the weight would be f of x2, and so on and so forth, all the way to the last term, which is going to be f of xn, the value of the function at the test point in the nth subinterval. So now we have this expression for our Riemann sum, where delta x is the length of each subinterval, and as we said, x sub I is going to be the test point in the ith subinterval. This Riemann sum will give a better and better approximation as n gets bigger and bigger. So when we have, say, only 10 terms here, we might get a decent approximation, but nothing special. When it's 100 terms, it's better still. When it's 1,000, it's better even than that. When it's 10 trillion, well, it's a very good approximation indeed. And if we take the limit as n, the number of subintervals, goes to infinity, which means that each subinterval becomes infinitesimal, we get the actual value of the integral. In other words, to get to the integral itself, we can take the limit as n goes to infinity of this Riemann sum. And in fact, in most calculus books, whose authors are leery of using infinitesimals, this is how a definite integral is defined in the first place. So what we are doing last, they do first. Either approach is fine, of course. They just reflect differences of philosophy, pedagogy, and so on. Oh, I want to point out something else as well. Typically, when you see this limit definition of a definite integral written down, this stuff would be written in sigma notation, which I'm guessing you're probably familiar with, but maybe not. So I will write it down and I will explain what it means right afterwards. So we could re-express this as this limit of this stuff. This is a capital sigma in Greek, and we use it to indicate summation over some index. So what it means is you take everything that it controls, and in that expression, one after another, you let I, that index, be every number from 1 up to n, every whole number, so that you end up with f of x1 times delta x, which is this stuff, f of x2 times delta x, which is this stuff, f of x3 times delta x, which is the next term, all the way down, stopping when you get to n, so you get f of x n delta x, like this, and then you add them all up, which is why we have all those sums right there. That's all sigma notation does. It just allows us to express things like this in a more compact form. And it's almost like in the limit, this sigma becomes the integral sign. They both accomplish the same thing, adding up lots of things of this form, but in this case a finite number, starting at 1 and stopping at n. And in this case, we're adding up infinitely many things of that form. This is why the integral is a weighted sum of infinitesimals, whereas the Riemann sum is a weighted sum of finite subintervals. It's only when we take the limit as that number of subintervals goes to infinity that it becomes an integral. So yes, an integral can be viewed as a limit of Riemann sums. And if I want to be very precise, what I should write here is that this integral of f from a to b is this limit of Riemann sums where delta x is 1/nth of the length of the total region of integration, and x sub I is any point, a test point in the ith subinterval. All right, now you know how you can use Riemann sums to approximate the value of an integral, and how if you take the limit of a Riemann sum as the number of subintervals goes to infinity, you get the integral itself. But this is not only important for numerical approximations or for atheists of infinitesimals who want to be able to describe integrals without involving infinitesimals. Riemann sums also have important uses in developing new ideas. This is because there are instances where Riemann sums and even limits of Riemann sums arise fairly naturally, and then we can recognize that we actually have an integral where maybe we didn't suspect one in the first place. And I will show you an example of this next. So let's discuss the idea of the average value of a function over an interval. Now this is a weird concept, so I need to explain what I mean by it. Everyone knows what is meant by the average, or more precisely the mean, of a set of numbers. For example, if you take 4 tests in a class, and your test scores are 75, 80, 85, and 80, your average test score, of course, is the sum of those 4 scores divided by 4, the number of the scores. And in this case, that works out to 80. Everyone knows how to compute such a thing, and how to interpret it too. This average just means that if we took all the points and put them in one big pot, which we then divided into 4 equal pieces, each piece would be 80. So we have the exact same total here as we have here. And so much for ordinary averages of data sets. What we're interested in here, though, is something different. Not the average value of some set of numbers, but the average value of a function over an interval. In some ways, it's a similar idea, but in some ways, it's different. I mean, if I have some function f defined over some interval from a to b, this function takes on a lot of values over that interval. Whatever the height is here at a, whatever the height is here, whatever the height is here, whatever the height is here, whatever the height is at b, and whatever the height is at every point in between. And there are infinitely many of those, which already poses a problem, because it's tempting to just say, well, take all the different values that the function assumes and take their average, add them all up and divide by the number of values that we have. But that won't work for 2 reasons. 1, how do we add them all up? There are infinitely many of them, because there are infinitely many real numbers in any interval. And then, even if we could do that, how would we divide by the number of numbers? We'd be dividing by infinity in some sense. So what are we going to do? I mean, we'd like to apply the intuitive idea of an average, but this seems to be beyond our capabilities. I mean, maybe the integration demon could do it, but how are we poor humans to accomplish these tasks involving infinity in 2 different ways? Well, once again, let's go back to being children who are trying to imitate the integration demon. It's true, we can't take all the infinitely many values of this thing, at least not in any obvious way, and then find their average just by summing them up and dividing by the number of them that there are. So let's pretend. Let's do a finite version of that problem. Let's take finitely many points in this interval, find the value of the function at those finitely many points, and average those. That we can certainly do. We could do that with 5 points, or 10 points, or 1,000 points, or even 1,000,000 points. Our problem is, how do we make sense of it? Well, you can probably guess what we're going to do. We're going to use the average of finitely many values as an approximation to the average value of the function over that interval, and then we are going to take a limit as the number of values goes to infinity. So let's see how this would work. First, chop our interval up into lots of pieces of the same size. How many pieces? 10, 100, 1,000? Who knows? Let's just say n pieces, each of which has length, let's call it delta x. And if we want to be more precise, since delta x is 1/n of the interval, we could say that delta x is 1/n of b minus a, the length of the interval. Okay, now what? Now we will let x sub I be a test point in the ith subinterval. Any point in the interval you like. So x sub 1 is going to be some point in that first subinterval. X sub 2, some point in the second interval. And so on all the way down to x sub n, which will be some point in that nth interval. Now we can say that an approximation to the average value of the function f over the interval ab is going to be the thing we obtain by averaging up the n values of the function at the n test points. In other words, we evaluate the function at each of our n test points, add up the results, and divide by n, the number of values we have up here. And while I'm here, let me condense this with a little bit of sigma notation. We can rewrite the top as the sum of all the f of x sub I as I runs from 1 to n. So f of x1, f of x2, f of x3, f of x4, all the way up to f of xn, and then add them all up. That's what we have right here. And of course, we are still dividing the whole thing by n. In fact, let me rewrite this so that instead of dividing this whole sum by n, I'm multiplying it by 1 over n, which of course is the same thing. Well, this is nice and compact compared to this, which shows the virtue of the sigma notation. And you know what? It's kind of reminiscent of a Riemann sum. It's like a Riemann sum without the delta x's. We've got the weights without the lengths of the intervals themselves. Hey, but wait a second. Maybe we can sneak those in. Because after all this 1 over n out here, n is definitely related to the lengths of the subintervals. So maybe I can get some leverage there. I mean, I've got 1 over n right here, and I've got 1 over n right here as well. I can solve for 1 over n down here if I divide both sides of this equation by b minus a. Then I will have 1 over n is equal to delta x over b minus a. So let me make that substitution over here. All right, at least I've got the delta x in the picture, even if it's not quite where I want it to be. You know, I'm going to need a little more room. So let me get rid of this intermediate piece. That's better. And in fact, I think my next step will be clearer to you if I take this factor out here and write it as a product of 1 over b minus a and delta x. Now let's think about this stuff. In fact, let's really just think about this stuff. I've got this sum right here of n terms. It might be a small sum if n is small, or a huge sum if n is huge, but it's a sum of many terms. And I am multiplying that sum by this factor delta x. Well, you know from your very first days of algebra how we can deal with something like that. We can distribute this factor delta x into each one of the terms of the sum, so that we would have f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. Or when you put all of that together, we'd get this. The result of that distribution is a sum of things of this form, f of xi times delta x, where xi is x1, x2, x3, x4, all the way up to xn. Good. And hey, that is very nice, because now the stuff I have in brackets here, that is a Riemann sum. So we are going to be able to use our knowledge of Riemann sums, namely their connection with integrals, to get some good information here. But before we do that, just take a step back and think about what we have established so far. We're trying to find the average value of a function over an interval. And we have determined that an approximation to that average value of the function over the interval is given by this expression right here. Now, for different values of n, in other words, different numbers of values of the function that we are averaging, we're going to get different approximations. In particular, the larger n is, the better the approximation will be. This is obvious. If, say, n were 4, and we just took 4 different values of the function and averaged them, we'd get a pretty lousy approximation to the average value of the function over the whole interval. If we did it with 40, we would get a much better approximation. If we did it with 4 million, we'd get a better approximation still. We're trying to sneak up on infinity, and 4 million beats 4 any day. Anyway, an approximation to the average value is given by this expression, which gets better and better as n gets larger. In the limit, as n goes to infinity, we achieve the exact average value. That is, the average value is the limit, as n goes to infinity, of this entire expression, which I will rewrite here. Now, what is that limit? Well, 1 over b minus a is a constant, so it just sits there. It has nothing to do with n. But this stuff in brackets, that is our Riemann sum. And we know that when we take this limit as n goes to infinity, what happens to the Riemann sum? It becomes an integral. So in the limit, all of that stuff becomes this. The constant just sits there, the Riemann sum becomes an integral, and at last we have something that we can compute. Let's clean up all this mess and summarize what we have found. The average value of a function f over some interval a to b is given by this simple formula, which in many respects should be reassuring. It's kind of like the familiar formula for an average. It involves some summation and then some division at the end. The summation is in the form of an integral of the function over the interval, and what we divide by is not the number of values, but rather the total length of the interval. So it's a very memorable formula to find a function's average value over an interval, integrate it over the interval, and divide by the length of the interval. And that's it. But what I really want you to take away from this is the way we derived that in the first place, which depended on knowing that a limit of Riemann sums is in fact an integral. Let's do a quick example, and then I'll say a few last words about average values. So let's find the average value of the squaring function over the interval from -1 to 2. It never hurts to think geometrically, so let's bear the graph of the function in mind. Well, our solution is simple. How do we get the average value? We integrate the function over the interval and divide by the length of the interval, which in our case is 3. And now we have a very easy computation. The antiderivative is x cubed over 3. Let's pull that 1/3 out to make it a ninth. Evaluating the brackets, we get 8 minus minus 1, which is 9. Multiply that by a ninth, and we get 1. Interesting that it came out to such a simple value, a whole number. This function takes on every real number value between 0 and 4, hitting all the ones from 0 to 1 twice, in fact, and the average turns out to be just 1. Now, there are some different ways to interpret average values of functions over intervals, and there's an exercise or two in the book that leads you through them, but I will mention one right here, leaving the full argument for it to you to do in the homework problems. One way I like to think about average values is as if our graph over this interval was the surface of some water sloshing around in a tank, where these are the sides of the tank at the edges of the interval. Now, if whatever disturbance gave us this shape of the water at this moment were to cease, and the water were allowed to settle to its natural level so that it would be horizontal, it's always going to settle at the level of its average value, which in this case we said is 1. So that means if we let all the water settle here, it would end up at this level, given by the blue line. And you can see very easily that that's going to be the case here, because we should have that the amount of water, the area under the curve, should be equal to the area under the straight line. Well, the area under the curve is the integral of the function between -1 and 2, and if 1/3 of the integral is 1, then the integral itself must be 3. So that means that this area must be 3. Well, is the area under the straight line 3? Of course it is, because it's a rectangle 3 units long and 1 unit high. So that is indeed where the water would settle in this particular case, and it will always settle to the average value of the function over the interval, whatever interval we are looking at. So that's a nice way of thinking of average value, and it connects to the notion of the average of just a finite set of numbers. I gave you the example before where you had the 4 test scores, and the average turned out to be 80. And they said, well, it was like putting them all in a pot and dividing it up so that we had 4 80s, and the sum of those 4 80s was the same as the sum of the original 4 test scores. Well, here what we are saying is that instead of all these different values of the function, we could in some sense think of the function only taking the value 1, its average value. And if we thought of it that way, the total, thinking of that total area under the average, would be the same as the total of all the values of the original function, namely the area under that curve. This notion of the average value of a function might seem a little esoteric. Why would anybody care about that? It has lots of applications, just as ordinary averages do. One nice one, for example, which is a little out of our reach because it involves multivariable calculus, but I think you can understand it, would be if we had, say, some two-dimensional shape, some region, let's say, of the xy plane, and we want to imagine this shape as being some homogeneous substance, a shape cut out of tin or whatever it might be. And we might ask, where is the center of mass of this shape? And the way we end up finding that is by computing a couple of averages. The first thing we do is we think of all the infinitely many points in that shape. And we ask ourselves, of all the points in that shape, what is the average x-coordinate? And let's just say that the average x-coordinate turns out to be here. Then we know that the center of mass, wherever it lies on that dotted line. And then we ask, okay, of all the points in this region, what is the average y-coordinate? Every point has a y-coordinate. What's the average of all those y-coordinates? And once again, we can compute that, and let's say it turns out to be here, then we know that the center of mass is going to lie on that dotted line. Well, if it lies on both dotted lines, there's only one point it could be, namely this one right at the intersection of those two dotted lines. So that would be our center of mass. Now, actually computing those averages, as I said, involves double integrals, which you haven't studied yet, but it's the same kind of idea. We chop the region up into infinitely many little squares like that, infinitesimal in both directions. We have a function that we evaluate at each one of those infinitesimal squares. This would just be the function that, for example, returns the x-coordinate or the y-coordinate for our two different computations. We compute the integral. We would end up dividing by not the length of an interval, but the area of this whole region, and we would end up with an average value that way. The details are unimportant. I just wanted to give you a sense of how it's used. You could also then generalize this problem to where the region is not homogeneous. It has a different density at different points. Or you could generalize it to where it is an object in three-dimensional space. And now you're getting into more realistic problems in physics and engineering. But for us, the main reason I wanted to talk about average value was to give you an example of how thinking about integrals in terms of Riemann sums, that we can think of an integral as a limit of Riemann sums, can produce interesting results. And that Riemann sums are not merely for approximation. Although approximation was still there, the way we came up with this interesting result was to begin by approximating it. We approximated the average value with an expression that we then massaged into the form of a Riemann sum. And then by taking a limit, that Riemann sum became an integral, allowing us to compute average values very easily. All right, that is it for Riemann sums, and I think that is going to be the last video for Chapter 6, and therefore of Part 2 of full frontal calculus. There is one more section in Chapter 6 in the book that I am not making a video on, at least not for now, called Escape from Flatland, which I think you will find very interesting. It's about the idea of hyperspheres, spheres in spaces of 4 and more dimensions. But that's all for this video series. If you are pushing further into full frontal calculus, I already have a series of videos for Part 3, which covers Chapters 7 and 8, so dig in. I'll see you next time, whenever that may be.